Have you ever wondered what would happen if the Earth just stopped spinning? It's one of those wild, late-night questions, but it turns out digging into it reveals some pretty profound truths about the powerful forces that shape our world. So, let's do it. Let's explore what would happen if the Earth stood still.
All right, let's start with the most extreme, most dramatic version of this scenario. Imagine our planet, after spinning like a top for more than 4 billion years, suddenly, and I mean instantly, grinds to a complete halt.
So, what would happen in that first second? Well, the answer comes down to a physics concept we've all experienced, but on a scale that is just mind-boggling: inertia.
You know that feeling when you're in a car that slams on the brakes? The car stops, but your body lurches forward? Right. Now picture that happening to the entire planet. The solid rock of the Earth stops, but everything else, the atmosphere, the oceans, you, me, every building, every tree, it all keeps going at its original speed.
And just how fast are we talking? Well, at the equator, that speed is around 1,670 kilometers per hour. That is way faster than a commercial jetliner. Everything, and I mean everything, would be scarred from the surface, launched sideways in a catastrophic supersonic wave.
The immediate fallout? It's almost impossible to picture. The atmosphere would effectively become a planet-wide blast wave, wiping cities off the map in a blank. The oceans, carrying unimaginable momentum, would surge across the continents in mega tsunamis miles high. And the stress on the planet's crust from that sudden stop would trigger earthquakes and volcanic eruptions on a scale that would make a Hollywood disaster movie look tame. It would be, without a doubt, a total surface apocalypse.
Okay, so that's the instant stop nightmare. But what if it happened gradually? What if the Earth slowly wound down to a stop over millions of years? Well, the long-term effects would be just as world-altering, fundamentally rewriting the entire map of our planet.
What's so fascinating is that our planet's spin literally gives it its shape. Right now, Earth isn't a perfect sphere. It's what we call an ellipsoid, kind of squished, with a bulge at the equator caused by centrifugal force. That same force pulls the oceans into an 8-kilometer-high bulge there too. But if you stop the spin, that force vanishes. Gravity becomes the only game in town, and it starts pulling all that water toward the poles.
And this is what you'd get. Our world would be unrecognizable. All that water migrating from the equator would create two enormous polar oceans, and the land left high and dry in the middle would form a single unbroken megacontinent stretching all the way around the globe.
And it's not just the geography that would change. If the Earth stopped spinning but kept orbiting the sun, a single day would last for an entire year. You'd have 6 straight months of relentless, scorching sunlight, followed by 6 months of deep, dark, freezing night. The temperature extremes would be absolutely brutal.
Okay, look, a sudden stop is pure speculation, a fun thought experiment. But here, right here, is where we pivot from sci-fi to hard science, because our planet's rotation is changing. It is, as a matter of fact, slowing down.
And no, this isn't some fringe idea. It's a well-documented scientific fact. As this quote from Esri points out, this is something that has been measured and explained for a long time. So what's causing it?
The main culprit, believe it or not, is our very own moon. Its gravity pulls on our oceans, creating the tides. And all that sloshing water creates a tiny bit of friction that acts like a brake on the Earth's spin, day in and day out. The technical term for it is tidal despinning.
Now, before you start worrying, the process is incredibly slow. We're talking about the length of a day getting longer by just 1.7 milliseconds every century. So yeah, we've got billions of years before we need to worry about a full stop. But this tiny, relentless change might be having a massive effect on our world right now.
And this is where it gets really interesting. This brings us to a mind-blowing hypothesis from the world of geology. Could this gradual slowing, this constant tidal braking, be the hidden engine powerful enough to move entire continents? Could it be the driver of plate tectonics?
To get how that could even be possible, we have to look deep inside the Earth. We've got this rigid outer shell, the lithosphere. That's the crust we live on. It's basically floating on a hotter, goopier layer called the asthenosphere. And right between them, there's a really special zone that might be the key to this whole thing.
Scientists call it the low-velocity zone, or LVZ. The best way to think of it is as an ultra-slippery layer, almost like a film of oil between two huge surfaces. And the theory goes that as the main body of the Earth, the mantle, is slowed by the moon, the slippery LVZ allows the rigid crust on top to decouple and just keep on drifting westward from its own momentum.
All right, so that's the theory.
A slippery layer lets the crust drift west as the planet slows down. But if that's really happening, we should be able to see the evidence all over the globe, right? Well, a study in the journal Tectonophysics lays out some really compelling data that seems to back it all up.
First up, let's just look at the direction the plates are actually moving. These red arrows show how the tectonic plates are flowing compared to the deep mantle below. And while they all move in different directions locally, when you zoom out, you can see a clear, undeniable global trend, a kind of mainstream flow that is pushing to the west.
The evidence gets even stronger when you look at subduction zones. That's where one tectonic plate dives down underneath another one. It turns out there's a huge systematic difference depending on which way they're diving. Plates diving to the west plunge down steeper and deeper, but plates diving to the east go in at a much shallower angle, and the mountains they build are way higher. This isn't just a random fluke, it's a consistent pattern all over the world.
And this diagram from the study just visualizes that difference perfectly. I mean, look at this. Each one of those lines is a tectonic plate diving into the mantle. On the left, you've got the west-directed plates, and they are plunging almost straight down. Now compare that to the east-directed plates on the right, which are sliding in at these really gentle angles. It's not a subtle difference at all. It's a huge divide in how our planet works.
And the numbers themselves? They're staggering. The average angle for a west diving slab is 65.6 degrees. For an east diving one, it's just 27.1 degrees. That's more than twice as steep. For a difference that massive and that consistent across the globe, you need a really powerful global force to explain it, something exactly like the entire crust slipping westward.
And for the final piece of the puzzle, check this out. This is maybe the most compelling evidence of all. That blue line tracks tiny, tiny changes in the Earth's rotation speed, what they call the length of day. The red line, that's the amount of energy released by earthquakes worldwide. And just look at how they mirror each other. When the Earth's spin slows down just a fraction, when that blue line goes up, we tend to see a spike in global seismic activity. It strongly suggests a direct mechanical link between our planet's spin and the stresses that cause the ground to shake. So it turns out our planet's rotation is doing so much more than just giving us day and night. It literally shapes our geography, and there's some really powerful evidence suggesting that its gradual slowing is the fundamental engine driving the continents, building our mountains, and rattling the very ground beneath our feet.
And that just leaves you with one final big question. We started with a wild what if, and ended up uncovering this massive, active force that's shaping our world in real time. It really makes you wonder, if something as simple as the planet's spin can do all this, what other huge cosmic forces are out there, quietly working on our world in ways we haven't even begun to understand yet?